All right, in this working example, we're looking at calculating the mass of the sun from the orbital data of our home world, the Earth here. But first, we'll define gravitational field strength. Gravitational field strength can be defined as the amount of force acting per unit mass, okay, force per mass. So on Earth, for example, there are 9.8 newtons of force that act on each kilogram of mass for an object sitting on the surface of Earth like this. So the Earth has mass and the object has mass, and the gravity field strength that's created by this object is felt by sort of the mass here, 9.8 newtons for each kilogram of mass that rests on the surface. We can calculate this value by considering Newton's second law of motion, F equals ma, and Newton's law of universal gravitation. Force of gravity is g times the mass of the two objects divided by their separation distance squared. If we equate these two things and solve for the acceleration due to gravity, we have that the acceleration due to gravity, which is the a in this equation, is equal to gm over r squared. So it's the mass of the Earth and the radius of the Earth that govern the value or the strength of the gravity field of all the objects resting on the surface. Okay, those are the two things that go into the calculation. Rewriting this equation, it's easy to see how the gravity field strength, this acceleration due to gravity, g, okay, is equal to the amount of force acting on each unit mass. So if there's a lot of mass sitting on the surface, then there's going to be more force felt by that mass, right? And so that force due to gravity we call weight, right? So more massive things feel more weight. The question goes on to read, explain why for changes in vertical position of a point mass near Earth's surface, the gravitational field strength may be considered to be constant. Well, I have greatly exaggerated the size of these masses that would be on the surface of the planet, right? And so the planet is much more massive than anything that would be on the surface. And you know, the height that you would lift some mass up to is going to be negligible compared to the radius of the Earth itself. So if this is the way that we calculate the gravitational field strength, where r here is the radius of the planet, in this case, the radius of the Earth, then the reason why the gravitational field strength g may be considered to be constant is because if we add a tiny height to the radius, it's not going to change the denominator too much. In other words, what we're saying is that the gravitational field strength g, which we can calculate as gm over r squared, where r is the radius, is just about the same as if we calculated it with a tiny change in height sort of above it. And that's because h is really small compared to the radius of the Earth. How do we know that it's really small compared to the radius? Because they say it's near the Earth's surface. So that word near is saying, okay, well, it's a tiny change in height. And so this is going to be about the same as this. And therefore, we can, you know, consider the gravity field around this planet to be just about the same. It may be considered to be constant for that reason. There's probably a more concise way to put that into your own words, which is kind of what you want to do with this. All right. Question goes on to read, the orbit of the Earth about the sun is approximately circular with a radius of 1.5 by 10 to the 8 kilometers. The time period of the orbit is 365 days, and we are to determine a value for the mass of the sun and explain the working. In order for something to move in a circle, a centripetal force is required to do that. And so the centripetal force given by mv squared over r is provided by gravity given by gmm over r squared, as we've already talked about. So we can set these two equal to each other. We also know that for circular motion, velocity is 2 pi r over t, right? The distance around a circle is the circumference 2 pi r. So the way I prefer to do this calculation is to solve for the velocity first and then make the substitution in over here. So let's kind of put all these ideas together. Centripetal force in general, mv squared over r, provided by gravity, gmm over r squared. Lowercase m cancels, this r cancels, and we have the velocity squared equal to gm over r, the familiar orbital velocity equation. Making the mass the subject here, we'd multiply both sides by r over g. And so we get the mass equal to rv squared over g. What's the velocity? 2 times pi times the radius, 1.5 by 10 to the 8. And then this kilo is another 10 to the 3, right? So really together, that's 10 to the 11. Some students will be comfortable just saying, oh, that's 1.5 by 10 to the 11 meters. But you can convert this prefix kilo just by memorizing that it means 1,000, right? And so that's going to give you the same thing in your calculator there. And then the orbital period is 365 days, but we want the SI units. And so there are 86,400 seconds per day. And this is the number of days for our orbital period, right? So days are going to cancel, will be in meters per second of velocity there. I'll show you all of the calculations here on the screen, the calculator, so you can follow along with your own calculator if you like. 2 times I times 1.5 times 10 to the 11th is that. So that's the distance in meters that we all travel every year. That many meters between birthdays. Divided by 365 times 86,400. And I opened up parentheses there. So now I can see that there's 31,536,000 seconds in a year, not accounting for the extra, sort of 6 hours for the leap day. When I hit this equals, I can see that the velocity for we Earthlings is 29,886 meters per second thereabouts. Substituting that value in over here, we can finally solve for the mass. And so we have a final calculation, 1.5 by 10 to the 11 meters. That's the radius r. The velocity squared, that number right there. Let me clean this up a bit. (29,886 meters per second squared. Don't forget to square that velocity. As I was grading some of your papers, we had dropped the square there, and we just had the velocity, but we didn't square it. So this v is squared, right, in the numerator there. And then g is 6.67 by 10 to the negative 11. The units here, meters cubed per second squared per kilogram. Those are the base units of capital G. And so here we can see that the meters cubed are going to cancel, all these meters. The seconds squared are going to cancel, and we're left with kilograms of mass. I still have the velocity in my calculator over here. So I'm going to square it. I'm going to multiply it by the radius of Earth's orbit, 1.5 times 10 raised to the 11. And finally divide it by capital G, 6.67 times 10 to the negative 11. You get a final answer of that, which is tough to read, so maybe I can change it to this form, exponential form, scientific notation. So we see that it's about 2.0 times 10 to the 30 kilograms is the mass of the sun based on our planet going around every 365 days at that distance. A different way to solve this would be to substitute these variables in for v here, and then make the substitutions for time and make the substitutions for r. That gets a little bit messier, but it more resembles Kepler's third law of planetary motion. If you're interested to see the calculation that way, click on the link above. This has been another worked example with Dr. Schleif, and we'll see you next time.